In the previous lecture, we talked about trap conversion gas and the first part of two branch lectures, which is conversion armaments. So in today's lecture, I'm going to be discussing the second lecture in this series, in this small mini series, and this is all about logistic growth. So if you have your books, turn to page 69. Very funny page. On chapter 4.4 or section 4.4, logistic growth and price of commodities. So, alright. So, numerous attempts have been made to develop models to study the growth of populations. One means of obtaining a simple model for that study is to assume that the average birth rate per individual is a positive constant and that the average death rate per individual is proportional to the population. So what we're trying to say is, every time we convert a person into a femboy, or whatever we want to convert them to, this conversion factor A is constant. It doesn't change. So, and that A is actually K in our previous lecture. A is K. And K is our conversion factor. So it tells us whether our conversion is going down or it's going up, if it's going twice as fast as we expected it, or twice as slow as we expected it. And so that's what we're saying. And then, so it says that the death rate per individual is proportional to the population. So every time a person stops being a femboy, so the average people stops being femboy rate is proportional to the population or the current amount of femboys that's converted. So if we have a P, if I'm gonna say S for stop. So S, the rate of S, ds over dt is proportional to the population, which is, well, P. If S tells us how many have stopped, the rate of change of stopping being a femboy is proportional to P with the factor K, directly proportional. They didn't say inversely, so I picked this. This is what the interpretation is. Alright, so if we let x of t represent the population at a certain time t, and the previous assumptions that I've made leads to the differential equation 1 over x dx over dt equals b minus ax. Or if I'm going to use dot notation, x dot over x equals b minus ax. I like using dot notation because it looks more cleaner and stuff like that, but just know that dot, I keep mentioning this, but I need you guys to understand that x dot is simply dx over dt. Likewise with theta dot. Theta dot is simply d theta over dt, the rate of change of the angle, right? Or angular velocity. Angular momentum. Alright, so B and A are positive constants. So the one that I wrote out, this equation, x dot over x equals b minus ax, is called the logistic equation. And the growth of population determined by it is called logistic growth. So it's sort of, yeah, so logics and stuff like sales, stuff like that. So I'm just gonna go by the book. We can separate the variables from here. I don't know, this is the 1 over x dx over dt. So, well, this is our x is our population, or the current amount of femboys we have right now, and then this is the rate of change of femboys, or well, the rate of change of the growth of it, right? This rate of change of the growth is equal to b minus ax. So we can separate the variables to get dx over x times b minus ax equals dt, and then we can integrate both sides now and get ln of x over b minus ax equals e to the c, nope, that's the second form, bt plus c, simplest form, no e's involved. But since this is an ln here, we can use e to cancel this out to get x over b minus ax equals e to the bt plus e to the c. Yeah, that's that. And since this is plus, you're really essentially doing this as plus. It's equal to it's really equal to just being e to the bt times e to the c, and that's form 2. Though that I accidentally wrote that a while ago. And so once we solve for x, we get the equation x of t, or a population function of x of t, b x of 0 e to the bt over b minus ax of 0, b minus ax of 0 plus a x of 0 e to the bt, where x of 0 is our population, or our initial population before we've done anything to them. Or actually, yeah, well, it really depends on the situation whether you guys are dealing with an unconverted population and you want to convert them, or an already completely converted population and you want to know when everyone's going to stop being a femboy, or when they're actually going to stop being femboys. That's the thing. So, yeah. So, yeah. An example of this differential equation is involving price and supply, the demand of a commodity. So D, S, and D are functions of time, and that the rate of change of the price is proportional to the difference between demand and the supply. Alright. So basically, this is just logistic growth right here. So it goes up, and it's really dictated by E, these kind of things. It's sort of like the previous one, chemical conversion, but it's more of on the more specific side of things, right? It's not just some vague differential equation. This actually gives us concrete stuff to actually compute logistic growth of a population. So let's do an example, right? I'm just gonna list the differential equation and the answer at the top as like before, so that you guys can understand. All right. So x dot over x equals b minus ax, and then our answer, x is equal to b x of 0 e to the bt over b minus ax of 0 plus ax sub 0 e to the bt. There, let's just erase this so we have more space. Alright, so suppose that we're given an initial population, so x of 0 is 50 femboys, say 50 femboys. Alright, and then let's say that happens at time 0. So our population is initially converted, and we want to know if these guys are gonna stop being femboys or they're gonna start growing in size. This paper fell. Alright, so yeah, so let's say that after let's say at t equals let's see at t equals 5 seconds, x of 0 becomes 51, right? Now, given these conditions, at what time exactly, we want to know, our goal, or the question is, at what time exactly is the population gonna increase to 60 femboys, right? Well, we can probably answer that by like literally looking at the time and doing some mental calculations, but let's solve it by calculus or differential equations and use a boundary value, solving to determine it, to determine the precise type that we get 60 femboys, right? So goal, when will x sub 0 equals, just x, this is x sub, when will x equal x sub n? When will x sub n equals 60 femboys? Alright, that's our goal or the question. You guys can take a moment to pause, but I'm gonna do this. Alright, so at the time 0, x is 50, so 50 equals b0. Alright, I'm gonna pick arbitrary constants for a and b. A is, let's say it's 2, and b is equal to 3. Arbitrary constants for a and b. So b is 3. 3 times 0, no, it's 50 actually. 50. 50. E to the b, which is 3, times 0, over, oh wait, hold on a minute. Oh wait, no, I'm sorry. This is not x sub 0, this is just x. So x, hold on. Yeah, we're trying to find t here. The variable we're trying to find is t, not some other thing. So it's b x here. Our unknown is t. That's so we're trying to find it at 51. Right? So 60. So that's 60 equals b sub 0, our initial condition, 50 times e to the bt, where b is actually 3, over, this is 3 minus 2 times 50 plus 2 times 50 e to the 3t. And what's the first thing we do? Well, we simplify this. So it's 60 equals 150 e to the 3t over 3 minus 100 plus 100 e to the 3t. And that's 3 minus 100. That's just negative 97. So 60 equals 150 e to the 3t. 97, negative 97 plus 100 e 3t. Right? So we're following. Just lower that a bit so you guys can see that. And so, first instinct is to divide both sides by the lower thingy here. So I'm gonna actually multiply both sides so that it becomes 60 times negative 97 plus 100 e 3t equals 150 e 3t. There. And then distribute 60. You have to get for this one. Okay. Distribute 60. So 60 times negative 97 gives us 5,820, negative 5,820 plus, well, 6,000. 60 times 100 is 6,000. E3t equals 150 E3t. And then we can just transpose the 6,000 to the other side. So, and then just subtract 6,000 from 150. And we get negative 5,820 equals negative 5,850 E3t. And so just divide both sides. 5,820, 5,820. Okay, wait. I'm gonna release the answer in the next video because of time limitations. Or yeah. So just stick around for the next video. If you don't really care about the complications and stuff, you can just move to the next lecture. So I'll see you guys then.